Hello, welcome everyone for this new lecture of CT111. So let's just get started right away. So to summarize, what we have learned previously is that there is a concept of information that is kind of succinctly characterized by this formula that information is negative log base 2 of the probability of a particular symbol. And the set of probabilities of the symbols generated by the source is that we have called the probability mass function, or the PMF. And we have seen that the PMF follows certain kind of intuitive notions regarding the probabilities, right? So probabilities can never be negative. They have to sum up to 1 and so on. And we looked at a specific type of random variable, which is actually a number, not a symbol, that the output of an information source can be mapped to. And so this random variable can then be associated with the expected value, which is given by this formula here. So this is the expected value of the random variable. And this is the variance of the random variable. Expected value kind of shows to us what is the most likely value that the random variable takes. And the variance tells to us the deviation, the jitters, the fluctuations that the random variable exhibits around this expected value. Okay. And then we looked at this notion of cumulative mass function, which is nothing but the integration of the probability mass function. We also saw that in addition to defining the information of a particular symbol, actually a quite useful and more an alternative metric which kind of captures the notion of the information generated by the entire source in a better manner is this entropy function, which is nothing but the expected value of the individual information values that are generated by the source, right? So that gives us this particular definition. Then we looked at a particular type of random variable, which is a binary random variable. It is, for example, a random variable that can be used to denote outcome of the toss of a coin. And for this random variable, we evaluated the mean value, which turns out to be nothing but the probability that the variable turns out to be 1. Right? So that probability is denoted as Q. And the mean of the variable is actually nothing but Q. Right? And the variance takes this particular expression. It is Q times 1 minus Q. The information for individual symbols, 0 or 1, is defined as negative log base 2 of Q and negative log base 2 of 1 minus Q in terms of bits. And finally, the average information is given by this formula. And we saw last time that if I plot this entropy function for the binary variable, it takes a particular form which is shown here. Basically, the entropy, the average information generated by the source, becomes 0 in the deterministic cases. So if either Q is equal to 1 or Q is equal to 0, which means that the source is completely deterministic, randomness associated with the source, then the entropy becomes 0, meaning that such a source which is completely deterministic has no ability to generate information. And that kind of makes sense, right? I mean, someone gave an example of the sun rising tomorrow. Probability of that happening for the foreseeable future is 1. And so that does not correspond to an informative event. Whereas if you toss a coin, especially when the probability that heads or tails come up is equal to 0.5, then such a source is the most information-rich source, because uh, it is least predictable. You can't kind of make any prediction ahead of time. And so corresponding number of bits generated by this source, every time you toss a coin, you get 1 bit worth of information on average according to the entropy function. And then for the other values of P, the generated information is smaller than 1. For example, if P is close to, let's say, I don't know, maybe 0.1 or so, right? So if P is close to 0.1, then this average amount of information generated by source is not 1 bit, but it drops to just half a bit. So that is the theory of information generation. Now somebody asked that how can information be generated in a fraction of a bit? A bit is either 0 or 1. So what does it make sense? How does it make sense to say that information generated every time you toss a coin is not 1 bit, but it's half a bit? So that is a good question. We are going to come back to it later. But let us continue this summarization that kind of captures what we have learned so far. So basically, we have defined the notion of an information generation source. And so far, we have kept the source to be discrete valued. It can be someone writing in English or Gujarati or Hindi, or it can be a camera which is taking a picture, or it can be when you toss a coin, or it can be the outcome of any binary experiment. So this is the type of discrete valued sources that this definition of information that we have seen kind of considers. And this definition kind of is intuitive to us. I mean, any time that you observe some outcome which is unexpected, you feel that it is kind of informative. It kind of captures everybody's attention. If India is playing against Zimbabwe in one-day international cricket, and if Zimbabwe beats India, then that becomes a headline in the next day's newspaper. Because it is unlikely that such a team will beat Indian team. But if the answer is typical, which is that India beats Zimbabwe, then it doesn't create that much information. Okay, so another aspect of this definition that we have seen, actually, if you think about it, it gives you certain numerical value associated with the information generation. And specifically, it says that if a particular event is highly informative, then the number of bits generated when that event occurs is large, right? So that is something quite unique. Today, when you download a video or when you store a file on your laptop, on your computer, the size of the video or the size of the file is measured in number of bits. And here we are saying that the more informative the event is, that particular event will occupy more number of bits in this particular day-to-day examples that we have of binary representation of the outcome of information source. Okay. Basically, what is happening is that the information is not being generated by a particular symbol, in fact. The underlying mechanism is the mechanism of selection. The source selects one symbol out of multiple possible symbols. That selection is the underlying mechanism by which the information gets generated. You can almost say that the source is the cause. It is the causation. It is the motivation for this particular symbol to get selected. And that selection is what is generating the information. And what is the average amount of information, or in other words, how can we compare two information generation sources side by side in terms of their ability to generate the information? Well, where this entropy notion comes into play. If you consider two sources, let us say one information source is that you pick any random hospital and you say that I'm going to just observe whether in the maternity ward the birth is of a boy or a girl. Compared to that, let us say that you say that I'm now going to do another binary experiment in which I'm going to sit in my balcony and observe during the month of March whether it is raining outside or not raining outside, right? So you will see that these both are binary experiments. The birth is also a binary event, boy versus girl. But there, the probability of a boy or a girl is roughly about equal. Whereas in the month of March, what is the probability that it is raining outside? It is pretty small. And so in an average sense, the first experiment is going to give you a higher amount of information on average. Basically, the entropy of that first binary experiment is pretty close to 1 bit per observation. Whereas the entropy of the experiment in which you monitor the rain events in March or April is going to be pretty low. Because most of the time it is going to be sunny outside. And because the probability that it is sunny outside is so high, the corresponding information that is generated is very close to zero. Maybe once in a blue moon, maybe it kind of becomes rainy, but then the probability of that is so small that it gets averaged out, and the average entropy still remains close to zero. So one way to think about it is, you think of your thermodynamics topic of your physics course, that you have a sealed container filled with gas. And if most of the molecules are not vibrating too much, maybe there are a few molecules which are jumping around a lot, then still the overall thermal energy or the temperature of that container is going to be pretty low because most of the molecules are kind of quiet. But on the other hand, when is this container going to have the highest possible energy or the temperature? Well, that is what the thermodynamics says, that for that to happen, you need to have all the molecules vibrating roughly about equally, right? So that is what this entropy notion captures also. For the binary source, what we saw is that if this probability of 0 and probability of 1 both are equal to 0.5, then you get the highest average information. And that generalizes to a k-array source. If suppose a source is not binary, but if it is having 4 symbols, then it turns out that when all the 4 symbols are equally probable, meaning that their probabilities are 1/4, that is when that source is generating the highest amount of information on average. Okay, so roughly speaking, you can think of entropy as giving the temperature of the source. Here, the temperature indicates the informativeness of the source. Okay, so that is one important concept that you probably want to keep in the mind. Okay, so we started out by asking this question that what is actually information and how to measure it. What is happening when a particular informative event occurs? I had asked you this question in your lab 1, and I saw over the weekend that some of you have given a good answer to that question. Actually, at least you have set your mind running and you have thought about it. Some of you actually just took this answer of entropy, but that I wouldn't count it as real answer because that is what I had already given you. So some of these questions, when I ask you, I would like you to do independent thinking on your own. you don't want to kind of repeat the answer that has been already given to you, or you don't want to kind of go and look at Google and see what Google says. Its main idea is to prompt you to think about some of these fundamental questions. And the answers that you come up with may be quite a bit different from the answer that then we would talk about in this class, but at least then you can contrast and compare what you came up with the answer that we will be studying. So anyways, we have looked at what the information is. We actually looked at the mathematical formulation and all. But you see, we kind of just appealed to the intuition. We didn't prove why information measurement in terms of negative log base 2 of probability is mathematically justified. But that is what Shannon did in his paper. We probably won't be looking at his mathematical justification in this course, but I want to just impress upon you that what Shannon did was even more deeper, and it was having a mathematical basis. He justified this definition of information by using mathematical arguments, and so that is something that I thought you should know. But anyways, after answering this first question, remember the other questions that we had asked was that how would you transfer the information? And what can happen when you are transferring the information, especially when the channel is noisy and so on. So that is the question that we'll be studying next. But as I said, in order for us to answer that question, which is really the tougher question of the two, I think it is better that we do a quick review of the probability theory, which is going to be quite similar to what you have studied in your high school, but it will have some hopefully new elements that you may not be fully familiar with, or those of you who are on the top of it, I think it will be a good revision. Okay, so before we get into the fundamentals of the probability theory, I thought that I will give you some example information sources. And remember, we have said that information source can produce any outcome, like boy versus girl, head versus tails, whether it is sunny or cloudy outside, like that, right? But we almost always will map those non-binary outcomes of an information source to non-numerical outputs of an information source to a number, and that number is called the random variable. And so now we are going to look at multiple such types of random variables. You can either just think of them as random variables, just probabilistic aspect to it, or you can think that these random variables are actually getting generated by an informative source. And so this would be a way to study the definitions regarding the information or the average information, the entropy, etc., to some different examples of information source. Okay, so we have considered one information source which is represented by this Bernoulli random variable. The other information source is a non-binary random variable. I mean, its output is represented using a non-binary random variable, because this information source doesn't produce just binary events. And the name given to this variable is called binomial random variable. And so binomial random variable is actually very simply defined. It is summation of total of n Bernoulli variables. Okay. So each of these xi's that are getting summed up are all Bernoulli random variables. So that is all there is to it. The only requirement is that this binary random variables which we are adding up, they have to be independent. Okay. What is independence? Let us wait for a few more slides. We will try to define that. But with this requirement satisfied, this variable y, which is nothing but the summation of this binary random variables, becomes the binomial random variable. Okay, so one quick question. What is going to be the minimum value of y? Any idea? What is the smallest value that y can take? Okay, so Kunj gave the correct answer. The smallest value of y is 0. Why? Because it is possible that all of these xi's are all zeros in a particular experiment. And so if you add up n zeros, you still get 0. So the smallest value of y is going to be 0. What is the next highest value of y? Okay, so Jill gave the right answer. The next highest value is going to be 1. The next highest value after 1 is going to be 2. Correct. That 2 happens when, out of this n variables that we are summing up, some 2, any 2, are going to be 1s and remaining n minus 2 are zeros. Finally, what is going to be the highest value of y? It is going to be n, correct. That happens when all of these xi's are all equal to 1. Now, the corresponding probability mass function is given by this formula. This is the PMF. And this y we just now saw, it takes any value from 0, 1, 2, 3, all the way up to n. And corresponding to a particular value of y, you plug in that value here, here, and here. And remember, capital N and capital P are given to you. And so then you can calculate what is the probability of that particular value of y happening. So this is the formula for the binomial probability mass function. Now you can calculate the mean, the expected value, and the variance, similar to what we did for Bernoulli, and it turns out to be n times p and n times p times 1 minus p. Okay, so this is a characterization of binomial random variable. Okay, now I'm going to go to something little new. And here there are two variables that I'm going to consider. And these variables are not discrete, right? So the two discrete variables that we considered are binary and binomial. They take discrete values. Binary takes 0 or 1. Binomial takes 0, 1, 2, 3 up to n. But a continuous random variable is one which takes any value along the real number line. And so when we are talking about the continuous random variable, this notion of PMF generalizes to PDF. This is called probability density function. And then there is a corresponding notion of cumulative density function or cumulative distribution function, which is denoted as f of x. So remember how we defined the cumulative mass function? Similarly, we are going to define cumulative distribution function for a continuous random variable as cumulative integration from minus infinity to x, small x, of the PDF, p of x of, let's say here I will put u, and then I'm integrating over u from minus infinity to x. So this is the definition of the cumulative distribution function, or CDF. And so corresponding to PDF for the continuous case, we have, corresponding to PMF for the continuous case, we have PDF, and corresponding to CMF for the continuous case, we have CDF. And they both contain the same data, right? So if you have the CDF, you can get the PDF by doing this type of differentiation. Whereas if you have PDF, then you can get CDF by doing integration, right? So that is the notion of PDF and CDF for the continuous valued random variables that we will study now. And it turns out that the PDF follows the same type of properties that we have studied for PMF. The probability density function can never be negative. If you integrate the PDF over the entire range of the real numbers, then you are guaranteed to get 1. Okay. And then finally, if you want to measure the probability that a particular random variable takes over a range of A to B, where B is greater than A, then all that you need to do is integrate the PDF from A to B. Or alternatively, like what we studied in the case of CMF, if you already have the CDF, then you can actually, instead of doing this integration, you can just do subtraction of the CDF function. And the subtraction will be, basically you will be looking at the CDF value at x equal to B, and from that you will be subtracting the CDF value for x equal to A. So this is the formula that you can use instead of doing the integration, in case if you have the CDF function with you. Okay, so these are the same 3 properties that we have earlier studied for the discrete valued variables. Possibly the only change is that the summation sign that was there, because the variable was discrete, is now replaced by this integration sign. Obviously, when the variable is continuous valued, then you can't do summation, you have to do integration. So with that as the main change, the other 3 properties are very similar. But there is one new property here, or I wouldn't say it's a property, it's more of an observation, which applies only to the PDF, only for the continuous valued variables. It doesn't apply to the discrete variables, which is that the PDF can actually become greater than 1. Okay, although this property 2 is always going to be satisfied. There is not going to be any violation to that. But if you examine the value of PDF for a particular value of x, it can be that it is greater than 1. Why it is greater than 1, we will take one example very shortly. But the point is that what this means is that the PDF value at any particular value, P of x at any value of x, is really not the probability. Okay, unlike the probability mass function, where if you take up any value of the probability mass function for any value of x, the value that you're going to get is always going to be the probability of that discrete variable for that value of x. So PMF always gives you probabilities, no confusion there. Whereas when you go to the continuous domain, there is a twist in the concept. The PMF generalizes to PDF, the CMF generalizes to CDF. The first 3 properties are going to be the same, etc., or at least very similar. You have to keep in mind that PDF, if you get a value of PDF for any particular value of x, it is really not giving you the probability of that value of x. And that is because the PDF can actually be more than 1. And the probabilities can never be more than 1, right? So that is something that I would like you to keep in mind. Okay, so this is the definition of CDF that we have already seen. I won't spend too much time on it, except to notice that, again, f of x is monotonically non-decreasing, which means that it always has this type of shape. This is allowed. This can happen. But what cannot happen is CDF behaving like this. So this cannot happen. The CDF function can never decrease. It can either stay same or it will increase. Those of you who like to spend time with the stock market, you may be thinking that it would be nice if the stock market also behaved like this, but apparently not. Stock market behaves more like this black curve, whereas CDF never decreases. And if you examine the value of CDF at negative infinity, no matter what random variable it is, no matter what informative source it is, the value is going to be always 0. And the value at positive infinity is going to be always 1. Can anybody say why f of minus infinity is 0 and f of infinity is 1? It is 1. If you know the answer to that, you can unmute and speak out.
Or maybe because f of minus infinity means that we are not adding up any probability, so it will be 0.
So PDF will be greater summation when always greater than 0, greater than or equal to.
I am not both answers are maybe partly accurate, but they are not complete. One very simple answer
Sir, can I answer?
that you can get based on this definition of CDF.
Sir, can I answer?
Yes, go ahead.
Sir, for f of infinity, we are checking probability for all random variables x less than infinity. This is true for all x. So if you will just summation of all the probabilities, so it will be 1. And for minus infinity, we cannot get any random variable that is less than minus infinity. So we are not getting any probability.
Yeah, so Tarang, I think you probably hit the right note. So yeah, basically, if you ask the question that what is the probability that a particular random variable is greater than infinity? A particular random variable is less than positive infinity. Obviously, the answer is going to be 1, right? I mean, a random variable cannot be more than infinity. It is always going to be less than infinity. So with probability of 1, it is going to be less than infinity, and that is why f of infinity is always 1. Similarly, what is the probability that a particular random variable is less than negative infinity? Now, nothing is less than negative infinity. Negative infinity means you are already at the left edge of the real number line, whichever it is. And so therefore, the probability of that happening is also going to be well defined. It is going to be 0. Okay, so let us move on. So similar to the mean and the variance for discrete values, the mean and the variance for the continuous values are defined in a quite analogous manner. Pretty much the only change again is that the summation got replaced by integration. And it turns out that if you have a particular random variable x and you pass it through some mathematical function g, right? G can be sine or cosine or square of x or cube root of x. It doesn't matter what function g is, but it has to be a mathematical function. The output of this function should also be a number, which is denoted here as y. And so if you want to determine the expected value of y, then this formula applies. Okay, so this is one mathematical formula that we'll keep in mind. Okay, so I think I have a mistake here. So I would say that this is the wrong chart. When I compiled this document, seems like I ended up using the wrong figure here. So please ignore this chart. This is entropy. Obviously, what I want to show is the PDF for one example random variable, which is called the uniform random variable. Okay. So how is the uniform variable defined? So uniform variable has a PDF which is given by this formula. So let me try to draw it here. So this is the real valued line. And there is some lower limit, which is A, right? Basically, what this formula says is that this random variable takes a value from its lower limit, which is A, and its upper limit, which is B. And outside of this limits, the variable is always 0. The probability that the variable takes a value outside of this limit, that probability is 0. So these are the two limits, A and B. And this is the random variable. So the way this PDF looks like is, if I, on the y-axis, if I plot PDF function probability of x, it is constant. So it looks like this. Maybe I should use a different color. Right. So if you consider values of x which are less than a, then the probability or the probability distribution function p of x is 0. And from a to b, it's a constant value. And then from b onwards, it becomes 0 again.
मेरी गाड़ी चोरी हो गई है जी। तुम्हारी गाड़ी से टकरा के एक घायल आदमी सड़क पे पड़ा था और तुम उसे वहां मरता छोड़ के चले आए। वो गाड़ी देख रहे हो, उसे गायब करना है।
Somebody needs to mute their.
एक्सीडेंट की रगड़ से जो पेंट होता है ना मोटरसाइकिल, उसका रंग आपकी गाड़ी के रंग से मैच कर रहा है।
Nikunj, what is going on, Nikunj? You're watching news or you're listening to the lecture? Okay, so the height of the PDF is going to be 1 over B minus A. That is what this formula says over here. Okay, now recall this property number 2. Does that property hold for this uniform PDF that I have drawn over here?
Yes, sir.
If you integrate the PDF for x equal to minus infinity to positive infinity, you're obviously going to get 1. Why? Because this PDF looks like a rectangle. And when you do the integration, basically you are measuring the area of the rectangle. And the area of the rectangle is obviously 1, because the width is B minus A and the height is 1 over B minus A. So that property is going to always be true for this PDF, because this area is going to be 1. Okay, now let us take some examples. So let us say that A is equal to 0.5 and B is equal to 1. Then what is going to be the height of this PDF? Yes. So Kadam said 2, which is correct. Height is going to be 2. So now that is where our earlier observation is seen to be correct, that if I ask you what is the probability that the random variable takes a value of 0.75, well, that probability at least is not 0, right? So that much you can say that yes, it's not going to be, well, I should take back what I just said. If I ask you what is the probability that the random variable is exactly equal to 0.75, then that answer you will have to give to me using this formula over here. This whole formula, you can use this formula. And I will let you think about it. I don't want that answer right away. But at least you can't just simply look up the value of PMF at 0.75 and say that that is the probability, because here in that case, it is going to be 2. And that defies the notion of probability, which has to be less than 1. Okay. So let us move on. So this is just an example PDF of uniform random variable. Now I'm going to give you some diagrams of the CDF of this random variable. And they look like this. Okay. This fortunately is the correct diagram. I didn't mess up here. But here I have taken 3 different cases of A and B. For this black colored random variable, A is -2 and B is 2. For the red one, A is 0 and B is 1. And for the blue, A is -2 and B is 1. And obviously, if you integrate that rectangle, you are going to get a straight line moving upward, which is what all these 3 colors are. And specifically, you will see that if I go to the left side of this real number line, I get a value of 0. If I go sufficiently towards the right, I get a value of 1. So this is what the uniform CDF looks like. I'm not going to spend too much time on this. You can just plug in the formulas and determine the mean and the variance of the uniform random variable. I'll give this as your lab assignment. So maybe that time you can do this exercise on your own. There is one more type of variable which I think you should be familiar with. Actually, most of the people, they are familiar with this bell-shaped curve, which is called the Gaussian PDF. Gaussian PDF is again corresponding to a real valued random variable. And it is given by, the PDF is given by this formula. Okay. And what is one nice thing about this Gaussian PDF is that you don't have to spend too much time finding out what the mean and the variance of this variable are. If you know the PDF, the mean value is sitting inside the expression of the PDF. And similarly, the variance is also specified in the formula for the PDF, which is kind of unusual. Typically, if you have the math formula of the PDF, from that, you may not be directly able to determine what the mean and the variance are, except if it is Gaussian. Now, whenever we plot either the PDF or the PMF or the CDF or the CMF, the y-axis is going to be this, the probability density function or the probability mass function and so on. And the actual variable is always going to be along the x-axis. That is something that you want to keep in the mind. So in case of the Gaussian distribution, this probability distribution function becomes maximum at its mean value. Okay, so for the blue case, the mean is 0, and so the PDF is at 0. For the red one, I made the mean equal to 0.3, and so the PDF peaks at 0.3. Sorry, not 0.3, 3. So the highest value of the Gaussian PDF corresponds to the mean value of that random variable. And then variance tells us how wide this PDF is going to be. So the blue one has a variance of 1, and so it is a little wider compared to the red one whose variance is smaller. if I make variance very small, maybe instead of 0.4, if I make it 0.04, then this red one will look like this. Sorry for my drawing problem. It's not the right way to draw it, but you get the idea, right? So it's going to be highly confined. So maybe I should say that in the limit that variance becomes 0, the PDF is going to be just a straight line. Okay, so, and that makes sense. When variance is 0, basically the variable doesn't deviate from its mean value. All the time it is going to be exactly equal to its mean value. And so therefore all the probability is going to be concentrated at the mean value. The density of the probability is going to be focused at the mean value. And so you just get an impulse, just a spike corresponding to that mean value. But as soon as you start having non-zero values of the variance, then that PDF is going to open up. And then you can integrate this Gaussian PDF and then you get corresponding CDF curves. And the observation again here is that you see these are monotonically increasing. They are never decreasing. And second observation is that they go from a value of 0 at minus infinity and a value of 1 at plus infinity. By the way, this is, unfortunately, I would put them in percentages. This is percentage. So when you multiply 1 by 100, you get maximum value of 100. But the actual CDF is always between 0 to 1. If you convert it into percentage, it becomes from 0 to 100%. So that is one observation. And then maybe the last thing that I'm going to talk about this Gaussian PDF is that there are some rule of thumbs. You know, these are something that you can memorize. You can kind of keep it on your thumb, so to speak, which is that what is the probability that the variable is within plus minus 1 standard deviation from the mean? And so that probability is going to be 68.26%. What is the probability that the variable takes value from relative to mean? It takes value from minus 2 times standard deviation to positive 2 times standard deviation. And that value is going to be close to 95.4. So it's pretty high. Basically, Gaussian variable, you can kind of trap it. With 95.4% chance, the value is always going to be within plus minus 2 standard deviation related to the mean. And if you go to 3 standard deviation, then you are almost always going to find the value there. Okay, so most of the values, 99.7% of the values that the Gaussian variable takes are going to be within plus minus 3 standard deviation related to the mean. Okay, so this is something that is quite nice about Gaussian PDF, that you can kind of predict ahead of time. Not the specific value that the variable will take, but the range over which the variable is most likely to be confined. Okay, so this is, okay, I thought it's an informative diagram, so I took it from this website. Something good for you to kind of keep in mind and even memorize. Okay, so let us see. So that was just giving you certain examples of the random variables. So you see, so now I'm going to get into a slightly different topic. So I'm done with both the examples of discrete as well as continuous random variables. Remember, we are doing this review of probability theory because we want to answer this question of how the information gets transmitted. We saw how it gets generated, but now we are asking the question of how it actually gets transmitted. And then what can happen in its transmission that can mess up the transmission of information. I mean, you know that it is very common that information transfer is unsuccessful, right? I mean, there are jokes which play with that, right? I can't think of a joke along those lines, but you know what? Someone asking for a direction, he would have said that I want to go to this particular place. If I go 500 meters ahead, should I take? I should take right turn. Am I correct? And so this person would have replied that yes. I mean, he would have said yes, take right turn, right? And the person would have heard it as no. And so then instead of taking right turn, he would have taken left turn. And then instead of going to where he wants to go, he would be going exactly in the opposite direction. So that is where yes turned into no. This person spoke yes, but the person who was driving heard it as no. And so the information transfer became unsuccessful. And it has consequences in the real world, right? So we want to kind of capture that aspect of information transfer. But before we do that, we need to kind of, all of us, we should be on the same page regarding specifically what the information deals with, which is, as I've said earlier, it deals with our beliefs. And the math for describing the beliefs is the probability math. So that is why we are studying this probability theory. And now specifically, we are going to be looking at two random variables simultaneously, right? The first random variable is going to be same as what we have studied so far. It is the random variable corresponding to the source itself. It is the random variable which will model yes or no answer given by the person giving the direction. Because the person giving the direction knows that the answer is yes. And so when he says yes, a certain amount of information gets generated, and how to capture that information is what we have already studied. Basically log base 2 of 1 over p. Now we are going to throw in another random variable which is corresponds to, and this is something that it may not be very clear to you now, but as we go along, hopefully it will become clear. This another variable will correspond to what the person who is driving his vehicle hears, right? So let us call the first random variable as x. Person giving the direction, saying yes or no, that is x. What the person hears, we are going to denote it as a new variable, which is y. And y also we are going to make it 0 or 1. So most of the time, hopefully, when you are in this particular situation, and let's say you are driving and you are asking somebody for a direction, and you say that, am I supposed to take a right turn going ahead? Person who is going to give you the direction, if he says yes, hopefully most of the time you will also hear yes. And so y is going to be hopefully same as x most of the time. But maybe while he said yes, maybe there was some bomb blast, or I'm just running out of the real world scenarios. But let's say maybe there was a big truck passing by, or there was some noise. And so you, although he said yes, you heard it as no. And so it is possible that y, which is the random variable corresponding to whether you hear yes or no, is different from x, right? And so that is why we are now going to start having two random variables. Basically, x corresponds to the source and y corresponds to the recipient of the information. And once we represent both these variables, then we can talk about how much information is getting transferred. So think along those lines, okay? And the answer that we are going to get is very pleasant. It's very nice answer. I think you will love it. But before we get there, Now, specifically that we are talking about two random variables, x and y. Remember, x is corresponding to the source, y is corresponding to the listener. And this happens all the time, right? If you're talking on the phone, x is maybe your relative or your friend, which is on the other side, and y is your own ears and your brains. And so most of the time, what the other person says, you are able to hear properly. But sometimes there is fading, sometimes there is echoes, sometimes there is some disturbance in the line, and you can't really hear what that other person is saying. So again, it is the same type of breakdown of information transfer that happens. So we are going to be looking at now these two variables, x and y. And there is going to be a notion of joint distribution of x and y. That is where things will become little interesting. So we will have to be understanding the notion of joint probability distribution function and conditional probability distribution function. And that is what I think some of you have already are quite familiar with, because you could solve that problem on coronavirus disease. But some of you may not be as much familiar with. And so I'm going to review the math of the joint PDF and the conditional PDF. And then we'll actually go on to the bias theorem from there. So that is the roadmap. Okay. But before we get there, let us start by kind of reviewing what some of the basic concepts of probability theory are. Okay. So you see, probability theory is a very, very rich subject. Actually, you're going to have a full class in the next year only on probability theory. And that class itself also will not make you complete expert on probability theory, right? People go on to do their postgraduate studies in the field of statistics and probability. So it's a very rich topic. But where does it start from? Well, in order for you to understand probability theory, the very first thing that you need to understand is how to define the probabilities. And so that, I think, you have been looking at, you've been studying the definition of probabilities, maybe from your early high school math courses. And a very common definition is this ratio of favorable outcomes to the total number of outcomes. So what is the probability that the roll of a 6-face die will have an even numbered outcome? And so the total number of outcomes are 6, even outcomes are 3, and so the ratio is 1/2, and so you say that this probability is 1/2. What is the probability that when you toss a coin, it comes up tails? Again, there are 2 outcomes, and the favorable outcome, which is tail, is 1 out of 2, and so the probability is again 1/2. So this is a typical way that you would have defined the probability. But maybe it's not very known to you that there is certain problems with this definition of probability. So the very first problem is that, you know, if the number of outcomes is infinity, then you can't use this definition, because you have to divide by infinity and then the answer that you get is meaningless. So that is one problem. But maybe even more fundamental problem is that this works only when the outcomes are equally likely. Suppose somebody makes this 6-faced die in a way, maybe that person is a gambler and he wants to win most of the time, so he kind of manufactures a die whose face number 1, 3, and 5 are not very likely to come out. Maybe he puts slightly bigger weight on even numbered face. And so no matter when you roll the die, most likely it will come up as 2, 4, or 6. Well, then the probability is not going to be 0.5 anymore. The probability that it will have even numbered outcome will be more than 0.5. So the standard formula won't work in that case. So then the mathematician said that, well, okay, we'll forget about that definition. We'll come up with a new definition, which is called this relative frequency definition. And what this relative frequency definition says is that you just run the probabilistic experiment a large number of times, let us say some n times, right? And you just count the number of times that a particular event happens. And so if this person is cheated in the manufacturing of this die, but if you roll the die maybe 10,000 times, and you count the number of times that an even number comes up, you will actually observe that out of 10,000 times, 8,000 of them turned out to be even. And so you can say that the probability of the die taking an even number is 8,000 divided by 10,000, 0.8. And so you got around with the problem that we were having on the previous slide, right? Basically, you compute this ratio NT over N, and then you say that this ratio is going to be my probability. Same way, suppose if you want to measure the probability that the coin will come up as tails, then you toss the coin again maybe 500,000 times, and you count how many times it comes up as tails, and you divide that number by 500,000. Now, this value of defining probability is fine, except that you have to let the number of experiment approach infinity. And then you have to measure the asymptotic value of this ratio. Okay. Now, that gives us another headache. The problem is that nobody has time to run infinity number of experiments. I mean, forget about infinity. You probably don't want to toss the coin even 10 times and find out what is the probability of tails. So we don't want to kind of repeat an experiment so many times. And the problem is that if you don't do that, then this relative frequency itself will be a random variable. Okay, so this is a little funny. You want to think about it. We are trying to define the probability. And with the first definition on the previous slide, we saw that it had some disadvantages. And so we are coming up with this new definition. The problem is that if we use this definition for finite number of experiments, then the number that you are calling probability, that number itself will be probabilistic. So what is an example? You toss a coin, okay, maybe after this class is over, you take a coin and toss it maybe 10 times. Are you always going to get five tails and the remaining 5 heads? No. When you do this experiment of 10 tosses, in some series of 10 tosses, sometimes you might get 8 tails and only 2 heads. Some other times you might get 3 tails and 7 heads. And so every time you run an experiment, you are going to get a different answer. Basically, that relative frequency as a ratio itself is going to be random. But if you are trying to define the characteristic of a random number and you end up getting a random number in back, then it's like you're back to square one. You can't define the probability by saying that the definition itself involves probability. Right? So it's a circular definition. So that is the problem with this definition. Okay, so actually the probability theory, even as late as 1920s and 1930s, had this kind of, what would I say, contradiction or inconsistency at its root, at its heart. Right? The mathematicians and statisticians knew that this is a problem, that we can't have a mathematically consistent definition of probability which makes sense. So then what one mathematician in Russia, what he said is that I'm going to kind of put all such practical issues under the rug, and I'm going to now just give some definition of probability which is going to be consistent. And I'm not going to answer the question of how you measure or how you come up with that probability. So he said that for a particular experiment, let us say toss of a coin, I'm going to say that the two outcomes will have some probability which we have defined earlier to be q and 1 minus q. And I'm not going to answer how you know what that value of q is. I mean, we know intuitively that for the coin that q is going to be 0.5. But how do we know that? Do we have experimental justification for that? No. Because if I run experiments 10 times or even 100 times or even 10,000 times, my answer is never going to be exactly 0.5. So experimentally, I don't know why that q is 0.5. But intuitively, I feel that it has to be 0.5 because, you know, both the sides are equally likely. So Kolmogorov said that I'm going to use the set theory, which you have studied again in your high school, and I'm going to now start associating probabilities to the sets. Okay, so that was his approach. That is where our next topic of joint probabilities, conditional probabilities will come into play. So what Kolmogorov said is that the most fundamental aspect of any question that deals with probability is this concept of atomic events. Okay. And then he said that there is a universal set made up of these atomic events. That is what he said. So let us picturize this, visualize this. So this is the universal set. And maybe atomic events would be like this, little dots inside. In this case, there are 4 atomic events. Right? And so now what he said is that if this is my set, the set has 4 atomic events as its members, then what are all the possible combination of events that can happen? And those combination of events are going to be subsets of this entire set. From your earlier math course, do you know for this particular set of atomic events, what is the possible number of subsets?
Two raised to power n.
Exactly. So in this case, it will be
16.
exactly. It will be 16. Very good. So Dhruv gave the right answer. It is going to be 16. Right? So he said that there are going to be 16 events, out of which one event is this actually entire universal set. There's going to be another event in which none of these 4 atomic events happen. That is going to be called null event. And then there is going to be remaining 14 events, which are going to be different subsets of this universal set. And what Kolmogorov said is that I'm going to assign a number which I'm going to call probability of that particular subset, that particular event. And that number, he said, is going to be always between 0 and 1. And so he said, I'm going to come up with a rule for doing that. Okay, so fine. Let us take an example. If it is a die with 6 faces, then the atomic events are that die comes up 1, 2, up to 6. These are the atomic events. Okay, and so the set of this universal set in this case will have 2 to the power 6, 64 possible events. Toss of a coin will have 2 atomic events. Either it is head or tail, and so on. The superset or the universal set is always going to be called a certain event. Its probability is going to be 1. And the set of outcome where none of the atomic events happen is called null event. Obviously, one of the atomic event has to happen, and so this null event has a probability of 0. Okay. Now we are going to talk about the subsets of this universal set. And associated to each subset, we are going to assign some notation. We are going to call that subset some event, right? So again, in the case of this in case of a set with 4 atomic events, which are given like this, if I call one subset to be made up of these 2 atomic events, that corresponds to that this particular event A happened. So for this A, again, let's say we don't want to assign a number to this event. We'll say that when A happens, we will actually say that A occurs, which is basically these 2 atomic events, the subset of these 2 atomic event has happened. When we say A occurs, we are going to assign a corresponding random variable. We are going to make it x equal to 1. And when A doesn't happen, which is these 2 atomic events, x is equal to 0. Now, somebody can say that, okay, that is your event A. My event is going to be different from your event, and that is this subset. And I'm going to call this as event B has happened. And so corresponding to event B, that fellow will say that I'm going to assign a random variable y. When this subset happens, I'm going to say that random variable y is 1. When this subset doesn't happen, meaning that this subset happens, its complementary subset, I'm going to call it a random variable y is equal to 0. Does it make sense? Okay, so that is how this Kolmogorov's definition translates to events and then to random variables. And now Kolmogorov came up with this 3 axioms of probability theory, which are similar to what we have studied in context of PMF. But there is one axiom, this axiom number 3, which is new. And we will be studying that. The first axiom says that probability can never be negative. The second axiom says that probability can never be more than 1. Okay. And what is this third axiom? This is the important one. So this is the important axiom, and that is what we are going to be studying in the next lecture. But before we do that, I want you to consider one example. This is what I'm giving to you as a thinking assignment. That let us say that somebody takes your poll, okay, the poll of your entire batch. And in this poll, the person who is taking this poll goes to each one of you and says whether you want to be part of the dance club that is there at this institute, or you want to be part of a sports club, or if you wish, you can be part of both. Or if you are not interested either in dance or in sports, you can opt out and you can say, I don't want to be part of either one of them, right? So let us say that X is going to represent the preference that students exhibit about the sports club. And so basically X is equal to 1 means that that particular student wants to be part of sports club. X equal to 0 means doesn't want to be part of the sports club. Similarly, Y equal to 1 and Y equal to 0 means the student wishes to be part of dance club or not. Now, what I want to ask you is that in this case, I'm already telling you that there are 4 atomic events. So what are these 4 atomic events out of this random experiment that can be performed? And then how to express X and Y in terms of those atomic events. So that is the thought exercise for you that I'm going to give you. We'll talk about this when we meet again on